So good morning, I'm Tabor, this is Alex, Helen, and Matt, and we're presenting our blue-green solution to the growing ethanol demand. We'll start off with a little bit of background. Renewable fuels are becoming more and more important as the energy demand in the United States grows, and by 2040 it's projected that the energy demand will have grown by 30% since the levels we saw in 2015, which wasn't too long ago. Transportation is a big part of that energy demand, but only 5% of that is met with biofuels. And when it comes to transportation, liquid fuels are more advantageous than a gaseous fuel like hydrogen because they're more energy dense and they're easier to store. It's not to say that advances in hydropower or solar or wind are bad. They just address electrical energy production and they're not applicable to transportation. So that's why we chose to go with a liquid biofuel. Liquid biofuels, the most two common are biodiesel and bioethanol. And we chose to go with bioethanol because biodiesel is often variable from batch to batch and it's often hard to characterize exactly all the hydrocarbons inside of a solution. So we thought it'd be easier to go with a single compound and really nail that down. And when we looked into bioethanol, we found that the most common feed source is corn, but there are some underlying issues with that. One of the biggest issues is the amount of land and water resources required to grow the corn. It can lead to deforestation. The lack of crop rotation can severely degrade the soil, making it almost unusable. It decreases the amount of food crops available because it's being used to grow corn instead of other food, and it can drive up the prices of the food that is available. So we think that one of the only reasons that this industry has been economically viable is because of how heavily subsidized it has been from the government and the large tax breaks. And as the population grows, these problems will only increase. So we set out to create a problem statement and asked, can we develop a process to grow bioethanol renewably that does not rely heavily on land and water resources? And before we started designing our process, we looked into some of the past and present companies. One of them is Joule Unlimited. They produce bioethanol directly from cyanobacteria, but they had an outdoor process and they relied on the amount of sun that reached the cyanobacteria, so they were constrained by the climate and the weather. Two other companies we looked at were Heliobiosis and Proterra. They used algae to grow starches and would later ferment those starches into the ethanol. But they quickly ran into contamination problems because microorganisms grow very well in sugary solutions, and as far as we know, they're still battling those issues. So a little bit about our initial ideas in the process design. First had to decide whether to ferment the sugars or to produce it directly. And based on the research we did previously, we decided to go with the bioethanol directly and just avoid the contamination issues. And we also thought about whether to use a batch process, and this was a good option if we had chosen to ferment the sugars, because we could do this all in one unit op. We could grow the cells, extract the sugars, and ferment them, but we realized there would be very poor light penetration in a mixed CSCR, so we went with a continuous manufacturing process, and we realized that this would also cut down on startup and shut down cost of time, and will also greatly increase the amount of light that could reach the organisms we're using, which is the most important part when you're trying to grow the bioethanol. So we decided to go with Cyanobacteria because this is not a eukaryote like some of our other options, and it means that they grow much more quickly and they're easier to genetically engineer.
So this brought us to our overall process objectives. So the overall objective we want from our entire process is to produce bioethanol continuously from genetically engineered cyanobacteria. So in order to achieve this, first we need to culture the cyanobacteria and maintain them at an optimal growth rate for the highest amount of ethanol production possible. And at the end of our process, we want that ethanol to be at least 99.5% pure. So in order to do that, in between these two steps, we need to concentrate the cultures, the cells, lyse the cell walls to extract the ethanol, remove the cell debris and other media materials, and then separate the water and ethanol in order to purify it. And then lastly, we want to prove that this process works with a pilot plant that produces 2 liters of ethanol per day, which is a good scale for us to be able to have lab space and walk-in hoods for all of our unit ops.
So here's sort of what our initial design looked like. I mainly want to focus on the last 2 blocks in this block diagram, which is the liquid-liquid extraction and the distillation. This was how we envisioned removing the water and media salts, and the organic coming out of the liquid-liquid extractor would go into a distillation column where the ethanol would be the bottoms product. So initially we thought this was a great idea because it was going to be very energy not intensive at all. We can recycle the organic solvent, and we'll use a light organic solvent in the distillation column. So we immediately started modeling this in ASPEN. Just for background, our feed that would be going into this is 90% water and 10% ethanol. We explored solvents such as methyl terbutyl ether, methyl ethyl ketone, methyl isopropyl ketone, and a whole bunch more. We looked at solvent to feed ratios that vary from 1 to 5, but no matter what we changed throughout this whole modeling process, we found that we could only recover 70 to 80% of the ethanol coming in the liquid-liquid extractor, and the organic layers were far too wet, 1 to 5%, and sometimes even more than that, water. So we had to do quite a bit of literature research to find something a little more suitable for our process. So we came across an extractive distillation that uses ethylene glycol to break the azeotrope between water and ethanol. And just to sort of walk you through the process, the feed, which is water and ethanol, enters the bottom of the first column hot, and the glycol enters the top of the column cold. And basically what happens is they cross paths in the column. The ethanol comes out the top, and the water and glycol come out the bottom. And the whole purpose of the second column is to recycle the glycol. So when we did model this, we were able to get 99.5% purity for the ethanol, which is the industry standard, and we were able to determine the optimal number of stages for both columns, which is 25 and 12 respectively. So now that we have an idea of how we can purify our ethanol and water, I just want to walk you through our final design PFD. It starts with a photobioreactor. As I showed before. After that, it gets concentrated, a lot of water is removed in the first tangential flow filter, which just really quickly is, it's a membrane that water flows tangentially across, and a pressure difference drives most of the water through the membrane, which concentrates it. After that, the cells will be lysed and the ethanol will be released into the solution in a lysis step. Then it will be followed by another TFF to get rid of the cell debris. And now that we don't have the liquid-liquid extractor, we need something else to remove the media salts from the photobioreactor. So we will be using an adsorption column to get rid of the heavy metal anions and cations. And then finally, the extractive distillation, which I mentioned before. So now we're going to get a little bit more in depth on the photobioreactor. So just a very brief walkthrough of what a typical photobioreactor looks like. It utilizes clear tubing, which is surrounded by lamps for a light source. The airlift is simply where there's a liquid-gas phase separation, where air and carbon dioxide can be bubbled through the solution. There's an outlet for the gas, and then there's also a recycle pump for the aqueous solution. So for our specific pilot plant, we're going to use 5 centimeter diameter tubing, which would end up being less than 50 meters of total length of the pilot scale. And at the moment, we have envisioned sort of what we're calling a coiled wall configuration. So if you can imagine tubing in a flat stack that goes back and forth, that way you can have lights on either side, so there will be light penetration from multiple angles. The lights are going to be red shifted for optimal cyanobacteria growth, and it's going to operate at near ambient conditions, low temperature, 1 bar pressure, and while we are explaining a batch recirculation system in this picture, this process is still fully continuous because there's an overall inlet and exit flow.
Okay, next we're going to talk about the calculations and the math we did using the photobioreactor to model it. So on the right you see an image of a batch growth curve. This is how cells grow in a batch reactor. You can see the part of the really high slope, that's the exponential phase of cells where they grow at the maximum growth rate possible. And in a continuous bioreactor, instead of seeing this growth curve, we can freeze the cells at one point in time along this growth curve. So for our bioreactor, we're going to keep the cells at the maximum possible growth rate so we produce as much ethanol as possible. We used the Minot model and solved those equations to get the optimal flow rates and volumes for our bioreactor. And we found the optimal dilution rate to be about 1.6 per day. We got kinetic parameters from the literature to figure out how to get these values for like dilution rate. There's a lot of control systems in our bioreactor. So here's just a snippet from our P&ID. You can see we have 4 inlets, that's carbon dioxide, air, medium, and water, which are needed for cells to grow. And we have a lot of controls on every stream going in and out. So the main parameter we're considering is the concentration in the photobioreactor. This makes sure we have enough cells growing so we get the right amount of ethanol coming out. And we're using optical density as a measurement. It's controlled in a cascade setup. We have, since we have a lot of light sources on our the tubing that Alex described earlier, there may be a lot of heat generation from that, so we have a heat exchanger to make sure that bioreactors meet at the right temperature and there's no overheating. And the pH is another important concern, so we're controlling the pH in the reactor by using the carbon dioxide and air, which are able to buffer the pH a bit. And these are really good for our process actually, because we already need the carbon dioxide and air to grow the cells. So by using the same components to control pH, we don't have to add any additional acids and bases to our process. Next, we're going to talk about the downstream operations, again, about after the reactor. So we have the tangential flow filters. The main purpose of these is to remove a lot of water from our process. This allows us to recycle the water, minimize the water requirements in our process, and we end up recycling over 90% of the water. Our cell lysis tank is where we rupture the cell walls, break them apart, and get the bioethanol from out of the cells and into a solution. We surveyed the literature and found a combination of enzymes and surfactants that can be used to break cells apart. Our adsorption column can be used to remove salts, and while we don't have a lot of salts in our process, it's really still a good idea to get rid of them before the distillation columns, make sure nothing gets clogged. And we've surveyed the literature, we found a lot of different options that we'd want to be considering, but right now we're considering using a modified cellulosic lignin packing. And we have our final step, the extractive distillation, where we can get the bioethanol to the right purity and recycle all of our ethylene glycol. Here's just an entire P&ID. It's pretty hard to see from there, but we'll just point out a few key things that you haven't seen already. So this arrow points to, we have a lot of recycle streams in our process. Here we're recycling the water back from the TFF into this bioreactor, and that saves 90% of the water, meaning we don't use that much water to grow our cells. Here we have, this is the recycle stream for our ethylene glycol. So ethylene glycol is the most hazardous compound in our process. We want to make sure we minimize its use, and by recycling almost 100% of it, we really prevent ourselves from using too much of that kind of chemical. And here we highlighted we have redundancies and safety built into our system. On the ethylene glycol stream, which is the most hazardous stream, we want to keep that under the most control. We have 2 valves in series to each other to make sure that if one valve fails, the other one's still there to make sure everything remains in safe operation. So for safety considerations, the first one we have is level control on our cell lysis tank. So we don't want to be spilling live cell culture all over the place, and there's going to be some enzymes in there that could break down cells. We don't want to get those everywhere. We have level control to make sure that it doesn't overflow, and we have containment tanks to make sure nothing gets lost. We're using fail open and fail close valves in the strategic places in our process to make sure nothing gets out to where it shouldn't. So we have fail close for inputs to the system so nothing else can go in if something goes wrong, and fail open on outlets of the system to make sure everything drains out of our process. We have redundancy in valves and control systems like mentioned on the previous slide. And we've been reusing and recycling our toxic materials as much as we can so we minimize the use of that ethylene glycol.
Right, so moving on to the economics aspects of our process. For raw materials, we mainly have the components that make up our cultures, the lysis buffer to break the cell walls, and also the ethylene glycol for our distillation system. For both the media and the lysis buffer, we were able to find recipes online so that we could make them in-house, which we found reduced the cost significantly of both of these. For the ethylene glycol, the recycle rate is high enough that it's essentially a one-time cost, so that's also a low cost. And then the cyanobacteria is, because it is a self-sustaining population, a growing population, we only need, that's a one-time cost as well. So that brings it to a very low cost of only about $4,300 a year. So production costs are our most significant costs for this pilot plant. Because we're at such a small scale, our waste treatment is pretty low for both solid waste, which is the cell debris, and wastewater. For utilities, we decided that the most significant cost by far would be to operate the distillation system. So we were able to use the economics tool in ASPEN Plus to generate a cost curve. So we ran the system at a higher capacity that ASPEN Plus likes to run at, and then extrapolated down to 2 liters per day to get $36,000 a year for those utilities. And then finally for rent, we decided we'd have lab space in Cambridge, which is a pretty significant cost, but we wanted to have access to the most scientists, investors, and biotech companies. So that's about $760,000 a year. And then our most significant cost is our payroll. So why is that payroll so high? It's because we decided the most important part of this project would be the team of people that are developing the technology over a 5-year project. So we came up with positions in our biology and chemistry departments, and then decided that for the first 2 years we'd hire 1 employee per position while we're ramping up and really starting up essentially, and then for the remaining 3 years as we're finishing up this process, we'd hire everybody on this payroll. The capital costs are going to be a lot lower, again, because we are a small pilot plant. So what we did was we took all the unit operations and were able to use the factorial method from the Tauler textbook in order to estimate the installation costs and then do a class 4 capital cost estimate on these. And we also included a couple non-unit operations, such as the autoclave and an incubator, because they'll be important for sterilization of the media and also for quality control, and are relatively significant costs compared to everything else. So this comes out to about $137 per year for our capital costs.
So now we're going to talk a little bit about how we're going to market our product and generate revenue. So we have a few different options. We can potentially sell this IP to a big oil company that's interested in biofuels. You could potentially sell this sell to a corn bioethanol plant that's interested in alternative feedstocks. And then partnering and licensing are still options as well. However, for continuing this project, we decided that our primary goal would be to sell to a big oil company. So basically, that leads us to the very difficult part of this project, which was the valuation of the intellectual property. So we started by selecting 3 companies that are all publicly traded and they only make corn bioethanol. We took their market cap divided by the total number of shares to get the company's total value, and then we divided that by the gallons of ethanol they produce to get a kind of dollars per gallon number for each of these 3 companies. We averaged these 3 numbers to get about 50 cents per gallon, and we theorized that a mid-sized company, which falls right in the middle of the three companies' outputs, would be 5 million gallons per year. So their worth would be their hypothetical worth would be $260 million. Now, for our pilot IP, considering the fact that there's going to be significant cost, time, energy, and resources needed for scale-up, we felt that 1/10 of that future value was what the pilot IP is worth right now. So that's a valuation of $26 million. Now, this valuation has one giant assumption in it, and that assumption is that our developed technology is going to be as efficient as the ethanol produced from corn, and that's really something that you can only find out in a pilot plant.
All right, so because of the nature of our project, we won't generate revenue for the first 5 years as we're developing this process and technology. So we'll need an initial investment of about $10 million to cover the production and capital costs that we discussed before. And then after this 5-year R&D phase, we'd hope to sell the IP for the $26 million that Alex talked about beforehand. So after these 5 years and with a standard 12% interest rate, we found our net present value to be about $15 million.
All right, so what are the conclusions we can get from this presentation? We found that a photobioreactor with a large recycle loop is effective for maximizing the cyanobacteria growth rate that maximizes the ethanol production. It minimizes land and water requirements since we recycle so much water, and we are an indoor process, so that has advantages over like corn, which takes up so much agricultural land. It's a continuous process, so it eliminates high startup and shutdown costs. Like a batch system may take weeks to grow the cells for the cell culture, but we don't have to do that. And we are able to produce bioethanol at 99.5% purity, which meets the specification for fuel. And our intellectual property is valued at $26 million. For future improvements to our work, we have a lot of ideas for improving the efficiency. So we can improve the ability of the cyanobacteria to produce ethanol. This is more genetic engineering work. It'll make it more efficient, make the bioreactor faster, get more fuel. We can improve the media and feed sources for the bacteria, which also will improve the yield from our bioreactor. And we can improve the efficacy of the lysis buffer to make sure we are really breaking every cell apart to get all the fuel out of them, not losing anything in the waste stream. And overall, these improvements together would reduce the material requirements of our process and reduce the costs, making us more profitable.
Questions?
Sure.
I noticed on your payroll you have co-op position.
Yes.
Yes.
For this university?
Yep, Northeastern
Yes,
Cox.
that's why
Yep.
we're in Cambridge.
And another one, with the autoclave, did you look into any outsourcing options for that? Because I know there are a bunch of companies in the Northeast that's all they do, right? So you send your samples to the autoclave. I don't know if it can be cheaper or whatnot, but I was just wondering if you okay that.
It'd probably be easiest to have it in-house if we're doing a lot of quality control, to just run things over to the autoclave and sterilize media and everything like that.
Okay.
But if we're in a lab space in Cambridge, we might also be in like an incubator space anyways that has, autoclaves in-house already.
Is it pretty typical for a biocompany to have an autoclave in their lab? I've never worked at one, but it is, okay.
Every company, every biotech company I've worked at has
Okay.
autoclaves. Yeah.
How long does your fermentation process in CSTR take? Is it?
So we're
I know it's not a batch, but I know it's continuous, but how long do you plan on running it at a time?
So it's not actually fermenting anything. The cyanobacteria are genetically engineered to make the ethanol inside of themselves. In terms of the actual rate that's coming out of the photobioreactor, do you remember exactly or roughly? It breaks down to 2 liters per day once all the purification happens, but in terms of volume, it's a lot higher because it's really, really dilute in the bioreactor.
Yeah, there's about 150 liters
Okay.
of solution, and most of it's water, and that's why we're recycling so much of it.
Any other questions?
Is that ethylene glycol that you're recycling through the top? You said you're recycling like close to 100% of it.
Mhm.
Are you going to try to clean it out and replace it at any times, or is it?
So I imagine that at some point during the year, even in like a full production, there'd be some sort of shutdown where you could either sort of purify, or re-distill it all at once, or use a lower recycle rate. So if you recycle 90% of it, you can have 10% being repurified at all times. We sort of looked into those two options. I think it's kind of dependent on what scale you run at. For small things, it's easier just to shut it down, get new glycol, and rerun it. But in a production facility, I think we'd probably do something like a 80 to 90% recycle.
You said ethylene glycol is the most hazardous chemical you're working with.
Mhm.
Have you looked into any alternatives? I know propylene glycol is far less hazardous material, but I don't know if it would work
So
in the process.
it doesn't break the azeotrope between ethanol and water as well. It's when you add that extra carbon, it becomes a lot more nonpolar. So
I was just curious.
yeah.
Any other questions?
All right, thank you.